A common theme in math is to extend concepts that work in one domain to a larger one, like extending the discrete to the continuous with the gamma function, or the finite to the infinite with limits, or the two-dimensional to the any-dimensional with matrices, all of which I covered or touched on in videos on this channel. It's always exhilarating whenever this is possible, as you feel like you're discovering a deeper layer of reality hiding beneath the familiar. But there are certain times when such extension is impossible, and even provably so, where a function is truly limited to its original small domain. Of course, this is an extremely broad and deep topic, and one that I have neither the knowledge nor the time to do justice to in its most general form. But seeing as there's so much emphasis, especially on this channel, on how math can be generalized, it seems healthy to take a look at where you can't. So in this video, I'd like to share with you a small example of where we actually have the tools to predict when a certain phenomenon definitely cannot be extended beyond its original domain. And it has to do with infinite series and a little concept called analytic continuation. Take a quick look at the infinite series 1 plus a half plus a fourth plus an eighth and so on. It's a type of series known as a geometric series, meaning any two consecutive terms have the same ratio, in this case 1/2, and its sum happens to be 2. You can generalize this to any ratio x to get the series 1 plus x squared plus x cubed and so on, which converges whenever x is a number strictly between -1 and +1, and its sum is given by the formula 1 over 1 minus x. So for example, with x equals 1/2, we get 1 over 1 minus a half, which simplifies to 2. But what's a little weird is this formula works even for values of x where the original series diverges. For example, with x equals 2, the series becomes 1 plus 2 plus 4 plus 8 and so on, the sum of all the powers of 2, which clearly diverges to infinity. But instead of diverging in a similar way, the formula for its sum simply computes -1. So even though the series itself isn't defined for values outside the interval from -1 to 1, the formula we found to compute it does. The formula manages to extend the function defined by the series beyond its original domain. But now let's change the series a little by deleting a few terms from it. Well, maybe more than a few. How about every term whose degree isn't a power of 2? So the series we're left with is the much sparser series x plus x squared plus x to the 4 plus x to the 8, and so on. This new series actually converges on the same interval, -1 to 1, as the original, and if we take a look at its graph, it looks more or less similar to the old one. But where the original series can be extended beyond the interval -1 to 1, this new series, built from the same terms, actually cannot. Try as you may, you'll never find a formula that can extend this function beyond -1 to 1 in a robust way. Something about deleting terms from the original series has fundamentally changed it so that it's no longer extendable. But what? For an answer, we'll have to take a trip into the complex plane. The kind of series we've been looking at are called power series, since they're an infinite summation of powers of x. You can think of them as a sort of infinite degree polynomial, if you like. If you've taken a calculus class, you probably know a few things about them, like how they always converge either on a single bounded interval, or else the entire real number line. This leads to the concept of a radius of convergence, which describes the distance from the convergence interval's center to its boundary, and is always equal to half the interval's length. The radius of convergence is completely controlled by the coefficients of your power series. Change the coefficients and you change the radius of convergence. So for example, the power series, whose coefficients are all 1, gives you the classic geometric power series 1 plus x squared and so on, which has radius of convergence 1. But change the coefficients to these, and now it has a radius of convergence of 2. And again to these coefficients, and now the radius goes to infinity, and it converges on the entire real line. The first time you see power series, you might wonder why there's such an emphasis on a radius of convergence. After all, it's just half the length of the interval of convergence. So why not just talk about the interval's length directly instead of cutting it in half to get a radius? Well, one reason is it makes a lot more sense once you make the jump into the complex plane. When you allow the variable x in a power series to take on complex values, the set of values where the power series converges is now a 2D region in the complex plane. And it just so happens that for power series specifically, this region always has the form of a circular disk. So for example, the original powers of x series we've been looking at, where the coefficients are all 1, converges in the complex plane for x values within the disk of radius 1, centered at the origin, 0. By the way, once you're dealing with complex number variables, it's customary to use the variable z instead of x to help remind us it's complex. So I'll be doing that from now on. Now, remember how the real valued function, 1 over 1 minus x, extended the domain of the powers of x series beyond the interval -1 to 1? Well, similarly, the complex valued function, 1 over 1 minus z, extends the complex powers of z series beyond the unit disk. In fact, it extends it quite a lot, to the entire complex plane except for the point z equals 1, which results in a division by 0. Before we go on, it's important to clarify what exactly we mean here by extending a function. Because of course, given any graph, you can always extend it by attaching whatever random squiggles you want to its dangling ends. But what we're referring to here is a very specific type of extension. Namely, the extension needs to have a derivative everywhere in the extended domain, including at the boundary where it meets the original domain. What's more, the derivative needs to work even for complex numbers. It's a little beyond the scope of this video to explain what exactly a complex derivative is and how it's different from a regular derivative. But you don't really have to know it for the main point here. So for now, you can just think of it as a much stronger notion of derivative that extends the real number version, but more tightly constrains a function's behavior. What's more, functions that have a complex derivative in a local area around every point of their domains are extra nice and well-behaved, and are called analytic functions. And the good news is, most familiar functions you've ever heard of are analytic, such as polynomials, trig functions, and exponentials. So loosely speaking, you need a function to be analytic for it to have anything like a normal-looking formula that describes it. So if we're looking to extend a function beyond its original domain, and have hope that it will be well-behaved and maybe have a nice formula too, we should probably require an analytic extension, what's known in the business as an analytic continuation. So going back to our power series, the complex function, 1 over 1 minus z, is an analytic continuation of the powers of z series to almost the entire complex plane. It has a complex derivative at every point, and within a neighborhood of any point in its extended domain. But the claim is the new series you get by deleting all terms in it except those whose degree is a power of 2, has no analytic continuation whatsoever. Let's see if we can start to understand why. We'll be comparing the series to the original powers of z series a lot, so I'm going to call it the gap series, since it contains a lot of, well, gaps between powers of z, and I'll denote it with the function g of z for short, and similarly denote the original powers of z series with f of z. As a first step to getting a handle on what's going on with the gap series compared to the original, let's try visualizing both of them. Now, complex valued functions can't be graphed as easily as real valued functions, since their inputs and outputs are both two-dimensional, meaning we'd need a 4-dimensional space to graph it in the traditional way. But what we can do instead is have each function transform a selection of points in its input domain to their corresponding output points by way of an animation. So what I'm going to do here is put down a polar grid in the middle of the unit disk, and then animate where the grid lines end up after applying f and g to every point in them. What you might call the image of the grid under each function. Let's start with f, the original nice series. The unit disk kind of unravels to cover about half the complex plane, and you can see how the pattern abruptly stops at this vertical line, which is where the analytic continuation of this function would begin. But now let's take a look at what the gap series does. Same setup, I'll start with a polar grid on the unit disk, and then move all the points in that grid to their corresponding outputs after applying the gap series function g. And... oof, well that's a delightful mess. The grid kind of explodes into a tangled web of grid lines. Not sure we're going to learn too much from looking at this. So how about instead of trying to transform the entire unit disk, we just transform a smaller piece of it? Like, say, the disk of radius 1/2. Ah, that's better. The transformation is a lot more tame. Now let's see what happens as we gradually increase the radius of the input disk toward 1. Alright, it looks like it's getting crazier the closer we get to the boundary. In fact, let's see what happens if I start with just a single small circle in the input space and gradually expand it to the outer rim. Oh yeah, that's the issue all right. In fact, it doesn't seem to matter what part of the input circle we use. If I limit the input circle to just a small circular arc, its image under the gap series transformation is an exploded mess regardless. So it looks like all the craziness is happening around the boundary of the unit disk. Which I guess makes sense, since that's where the series switches from converging to diverging. But contrast this with our original series f of z, which stays well behaved even up to the boundary of the unit disk. Its image approaches being a vertical line. So somehow, deleting terms from this series has caused it to grow uncontrollably for inputs near the outer rim. But why? Let's start by visualizing the individual terms of both series with a chain of arrows. We'll start with the original powers of z series f of z. This blue point will refer to our input z value into the f series, and I'll draw out the terms of f as a chain of arrows placed tip to tail, where each arrow represents one complex number term of the series. Now obviously I can't render an infinite number of arrows on screen, so for this animation I'll limit it to around 25 arrows, which should be enough to reveal what's going on. With z placed at the origin, 0, there's only one arrow visible, the single unchanging arrow representing the constant term 1. But as I move z around, you can start to see the contribution of the other terms. We get a kind of spiraling chain of arrows, where the angle difference between each arrow is always the same, but each successive arrow is shorter than the one that came before. This reflects the fact that successively multiplying a point by a complex number z causes it to rotate by the angle z makes with the positive real axis. So for example, this arrow, representing the fourth power of z, is 4 successive rotations of the original z's angle. And the arrows are getting shorter because higher powers of z have smaller magnitudes, since the magnitude of the original z was less than 1. To see why the original f series is so well behaved near the boundary, take a look at how it behaves as the input point z approaches a certain special complex number on the unit circle that I'll call w, where w is a solution to the equation w to the 8 equals 1. Of course, one such solution is simply 1 itself. But remember, we're in the complex plane here, so this equation actually has 8 different solutions that are spread evenly around the unit circle. These points are known as the 8th roots of unity, since raising any one of them to the 8th power gives you unity, or 1. For this example, I'll take w to be this one counterclockwise step away from 1. As I extend our input point z from the origin toward w, the chain spirals inward more slowly, since the arrows are shrinking more slowly, until finally, as it reaches w, the arrows don't shrink at all anymore, and it becomes just a polygonal chain of arrows forever spinning in a cycle. In fact, it forms a regular octagon, which should make sense since raising w, an 8th root of unity, to higher powers will just result in rotations that are multiples of an 8th of a full turn. Multiply w 8 times in a row, and you'll get back to where you started, the number 1. Of course, this is a divergent series because the arrows just keep going around in a cycle without approaching anything. But at least it's not exploding off to infinity. In fact, if we nudge our input point just slightly away from w, the arrow chain now spirals in toward the center of the former octagon, even if it does so very slowly. So even though the series technically diverges at W, it seems like it kind of wants to be the center of mass of the octagonal cycle it forms, giving us a way to extend the series to W. But now let's see what happens if we try this with the gap series G. Same setup, I'll start with our input point at the origin and gradually slide it toward W, our 8th root of unity. Huh, that's strange. Instead of forming a kind of polygonal spiral orbit, the chain kind of straightens out, eventually becoming just a straight line chain heading off toward the right. Why would it do that? Remember that each arrow in the chain represents a different term in the series. In this case, it's the gap series G of Z, whose terms are z, z squared, z to the 4, z to the 8, and so on. In this case, each term in the series is the square of the term that came before it. Z to the 4th is z squared, and z to the 8th is z to the 4th squared. But for complex numbers, squaring them results in doubling the angle they form with the positive real axis. For example, the complex number I makes a 90-degree angle with the positive real axis. So squaring it doubles that angle to 180 degrees, placing it at the number -1. But in this case, our z is approaching W, an 8th root of unity. And since 8 is a power of 2, it means that if we square W enough times, we'll eventually get W to the 8, which is just 1. And after that, we'll be stuck at 1, since squaring 1 just results in 1 again. Or to put it geometrically, since we're starting at an angle which is an 1/8 of a full 360-degree turn, repeatedly doubling this angle will eventually turn it into a multiple of 360 degrees. After which, it stays stuck as a multiple of 360, since doubling a multiple of 360 just yields another multiple of 360. This causes the terms in the gap series to synchronize directionally, making the sum explode toward infinity. In a sense, since the gap series contains only powers of z that are a power of 2, its terms kind of constructively interfere with each other as z approaches an 8th root of unity, whereas the terms of the original power of z series, f of z, destructively interfere to converge toward a stable value. But here's the key point. There's nothing that special about the 8th roots of unity. This same constructive interference phenomenon will happen for the 16th roots of unity, and the 32nd roots of unity. In fact, the gap series, G of z, will explode as z approaches any power of 2 root of unity. And the collection of all power of 2 roots of unity forms a dense subset of the unit circle, meaning every point on the unit circle either is itself a power of 2 root of unity, or is arbitrarily close to 1, in the same sense that every real number either is a rational number, or is arbitrarily close to 1. So the unit circle contains a dense forest of singularities that cause the gap series, G of z, to blow up toward infinity. Still, not every point in the unit circle is one of these poisonous points. In fact, most are not. So perhaps it's still possible to analytically continue G past them by kind of threading the needle between the forest of singularities? But here we hit a fatal snag. Remember that analytic functions are those that have a complex derivative at every point in their domains, as well as within a local neighborhood of every point. So to analytically continue G to a point on the unit circle, we'd need, at minimum, for there to be some local region around it, however small, where G stays bounded and doesn't blow up. But any such region, no matter how small, will contain some of the poisonous power of 2 roots of unity that do cause G to blow up. Thus, no analytic continuation is possible to any point on the unit circle. The gap series is truly trapped there, hemmed in by a forest of infinite singularities. That completes our proof for this particular gap series, but you might also be wondering what other power series, or complex functions more generally, fail to be continuable beyond their initial domains. Again, big topic, but there are a few theorems that further generalize the result we got here to other power series that have gaps between powers of z. The first and simplest is known as the Hadamard gap theorem, which says that if a power series has gaps between powers of z that grow at least as fast as a geometric sequence, then it cannot be analytically continued beyond its convergence disk. This tells us that the specific pattern of powers of 2 sized gaps is not the critical thing at play here. That really, it's about how quickly the gaps grow, not that it precisely follows a certain pattern. It also tells us that the coefficients in front of the powers of z don't make a difference. It's only the speed at which the gaps between powers of z grow. It turns out, though, that this theorem can actually be strengthened quite a lot. The gaps don't actually have to grow as fast as a geometric progression. It's actually enough just to have them grow faster than all linear progressions. So for example, the gaps can grow as slowly as n to the 1.5, or n to the 1.001, or even n log n, or n log n, since all of these sequences will eventually outpace any given linear progression. And so all series that have such gaps will not be analytically continuable beyond their convergence disks. This fact is known as the Fabry gap theorem. And in a sense, this is about the strongest possible gap theorem you could hope to get, as another result, known as Polia's theorem, tells us that if the gaps grow slower than some linear progression, then it's possible to pick coefficients for the series that will allow it to be continued beyond its convergence disk. I won't go through the proofs of these theorems in this video, though if there's enough interest, I could perhaps do a follow-on at some point. Anyway, that's a little glimpse into the world of complex analysis and the nuances of analytic continuation. I think it's pretty neat that we're able to understand at any level how the seemingly magical process of generalization and domain extension works. It's sort of like metamathematics, using math to understand how math works. Kind of wild we can do that at all.